All right, everyone. So as I told you, I'm going to show you the graph or the graphical representation of the Solow growth model. And also I'm going to go over the mathematical example. So again, as I wrote to you on the previous video, we said that in order to reach a steady state, whatever you add is equal to whatever you subtract, right? So as the example that you have on the textbook, the inflow of water is equal to the outflow of water, so the change in water is going to stay constant. So in order to make the change in capital constant, the I, which has a positive sign, has to be equal to dk, which has a negative sign. If the positive equal to the negative, then the change in k is going to be 0. Or the change in capital accumulation, or we call it capital to labor ratio, is going to stop, is going to be equal to 0. As I wrote to you in the previous video, we said that we can always write investment as saving ratio multiplied times the function of k, which is also y. Okay, so you can write it as a small s times fk or a small s times y minus the depreciation ratio multiplied times the capital to output ratio. So in the steady state, as I said, the change in capital is equal to 0. So it's easy to see that on the graph. So if we have the depreciation function is equal to dk, then it's a constant, right? It's a constant line that is coming from the origin, such that if the capital to labor ratio is equal to 0, then we're going to start from 0. So depreciation is dk. If the k is equal to 0, then the whole thing is going to be, which is called depreciation, the whole thing is going to be equal to 0. So this variable is the d, which is equal to d times k. If the k is equal to 0, multiply times whatever ratio we have, this thing is going to be equal to 0. So we're going to start from the origin. So the blue line is called the depreciation, which is dk. Don't get confused between depreciation and the small letter d, because the small letter d is just the ratio, but depreciation is an amount in dollars. Okay, so the blue line is the dk, d multiplied times k, and then the dark red color which is the curve, is called the investment. And as we said on the slides or in the textbook, this investment function increases at a decreasing rate. Okay, so we have diminishing marginal return represented by the slope of this investment function that is at first is increasing. It's actually all the time is increasing, but it's increasing at a decreasing rate. So whatever you're adding is increasing investment, yes, but at a smaller and smaller and smaller rate. So in order to be able to get into the steady state, which we call it K star, then whatever you add has to be equal to whatever you subtract, right? Whatever you add, which is I, has to be equal to whatever you subtract, which is depreciation. Okay, this one is written as dk, and this one is written as s, small s. I'm sorry, it's just, so the small letter s times y, or you can write it as the small letter s times fk. It's the same thing. So we can reach the stage when the two are equal. We can also see it on the table. So in this table, you're given that y is equal k to the power third. Make sure that on the slides of the textbook that you have posted on week 5, you can see that this one has an arrow and a star, so it's basically, it's to the power. Okay, so there is a typo. Small s is the saving ratio, which is 45% out of your income is going to savings, or you can think of it as 55% of your income is going to consumption. 5% is the depreciation ratio. Your initial capital labor ratio that we're going to start with in year number 1 is $8. So we start with $8. We have income of 2, 1.1 out of it, which is 55% going to consumption, 45% going to, right, the savings. So 45% times 2, S times Y will give you this number. D is the 5%. 5% times K, 8, will give you this number, right? And then you're getting the change in capital from this equation. So the change in capital is the amount of investment minus the amount of depreciation, right? So you need basically to get S times F, or S times Y, which is the 9, minus the DK will give you this number. So the last, like this column with this column, like subtract this from this one, will give you this one. I, right? I multiplied times, subtracted from DK, or I'm sorry, DK subtracted from I would give you the change in capital. And then you keep doing the same thing for each and every row, okay? Until we reach a certain equilibrium that we're looking for. We're looking for this one to be equal to this one such that the change is equal to 0. This is the indication of a steady state that we're looking for. So if you're giving numbers and you are trying to find when an economy is going to reach a steady state, then your answer is going to be based on an equilibrium between these two. Okay? As I said, these two, you can say this one is I, has to be equal to dk. And when I is equal to dk, right, then the change in capital will stop moving or equal to 0. And this is achieved at a certain amount of production for this economy, which is $3. This is a very simple example. Okay, so a $3 is the steady state level of output. 1.65 out of that is the steady state level of consumption. And of course, 3 minus 1.65 will give you the steady state level of savings. Okay, and then 1.35 is equal to the amount of depreciation. This is the equilibrium point at which we have no change in capital. Okay, so we can also have it mathematically, like by computing the steady state values of K and Y. You can also have a question about K and Y and C and S, consumption and saving, like all the variables that you have. So it's easy because we are given this equilibrium, right? And the question will give you all the information, and one is going to be unknown that you need to solve for. So you're given that saving ratio multiplied times f of k, which we call it y, is equal to a depreciation ratio multiplied times k star. You can keep like rewriting this equality, which consists of 4 things. You can rewrite it such that you can write it as k star over s f of k is equal to saving ratio over depreciation ratio. Okay, so since we know that f of k is, this is actually k to the power third, so this arrow, don't get confused with this arrow, is just a typo. So this arrow is simply a typo, and this one is basically supposed to be like this, k to the power third. So you're given that f of k, which is this one, is given to you, right? It's basically k to the power third. You're given s is equal to 0.45. You're given d as being equal to 0.05. So given this, you can solve for k, right? And you have the details here. So you have k, you can substitute f of k for k to the power third, and then you can solve for k equal to 9 to the power 3 over 2, which is equal to 27, right? So k here is basically equal to 27, right, dollars for per worker. This is the steady state capital labor ratio. Okay. Graphically, we said in the first slide, we said this is the level that we want to reach, which would give us an equilibrium between investment and capital D depreciation. So this whole thing, write it as investment. This whole thing is depreciation. Those are in dollars. Those are not percentage, right? Those are in dollars. So you reach a certain level in dollars for the capital labor ratio. We start to kind of challenge this graph. Like from this point onwards on this chapter, which is chapter 6 of your textbook, we're going to challenge the graph. Like change things in the graph, change variables in your model and see how the graph is going to change. One of the things that we want to change is what is the impact of savings or saving rate on the steady state. To answer these types of questions, you have to be aware that what are the variables that are going to affect the slope and what are the variables that are going to affect the intercept. Okay, so as you can see here, the savings is just here, SF of k. If I change the saving ratio, it would affect this line. Okay, so it would affect this line, which is SF of k, or the kind of dark line. So when you check here, the change in savings would affect this dark red line and would basically result in a shift upwards. An increase in savings means an increase in investment, and how this is going to affect my investment function, it simply is going to shift upwards. And it makes sense that if people save more and other people are using these savings by demanding it and investing it into different investment projects, that this would lead to an increase in capital labor ratio. Okay, and of course it makes sense that if there is an increase in capital labor ratio, then it makes sense, like basically from the equation, if k increases, y would increase. But this doesn't have to be always the case because we still have other factors. Okay, so we have to think about other factors. We only don't have like savings here. We just, as we started this topic, we said we have savings, we have population, and we have technological change. So those are the three factors that would affect an economy to grow, and we're just explaining one of them. Okay, so based on this graph, K would increase, output would increase, but we want to know what also other factors that needs to be taken into our consideration. I'm going to stop here. I'm going to send you another video on the other factors affecting output.